I'd just like to take this opportunity to welcome everyone to our weekly seminar sessions. Today, Prof will be speaking to us specifically on knowledge representation and more particularly bad experiences with knowledge representation. And I think this is a topic that is relevant to all of our studies. It is something I think that as we go on and work within our projects and within this field, we will have to understand quite deeply. So yeah, I think Prof is very well known in this group by all of us. But just if anyone is watching or tuning in or just looking into our seminar, so Prof Randhir is an associate professor in chemical engineering at the University of KwaZulu-Natal. He's been lecturing for many years and has extensive experience in the application of AI, machine learning, and data science with respect to engineering projects. So yeah, I'll just hand over to Prof.
Great, thanks so much for that, Josh. Okay, so I guess the title is a little bit clickbaity because it's not all been bad experiences in this area. But before talking about that, I guess I've been saying it for a number of seminars now. Quite often I've been finding myself saying, can we formalize this somehow? How would you classify what you're doing? How would you relate that to the other studies going on? And so when I say knowledge representation, that's actually a very specific way of looking at it. And in this presentation, I'm actually going to talk about it a bit more generally. So I'm not going into formal areas of knowledge representation like ontology or first order logic and things like that. We're just going to talk about some principles to begin with, because it actually starts to suggest a kind of exercise that we can undertake. And I'll describe what that is as we go. So as I say, a lot of this presentation is motivated by just the sense that we need to formalize what we are doing a bit better. So this presentation is not quite about some piece of work where I'm going to present, quite technically. It's going to be a broad set of principles, and I hope we will formalize that over time. Okay, so going into it, part of the motivation is also because the field we are in has many people wanting to claim many things, and you see. In a field like artificial intelligence, everybody wants to use that as part of their advertising and things like that. With the result being that there are many articles out there which can be quite misleading in terms of what's possible and what people claim they can do. So we want to really treat what we are doing much more rigorously and be able to classify what we are actually operating on and the methods we develop. We want to be more rigorous in terms of understanding how it places against the problem that's being solved. And just to give one example, think about how modestly the field linear algebra is titled. Right, linear algebra, it makes you almost not want to study it. You think, are we just studying straight lines? Is it only going to apply when my equations are linear? And actually, if you think about something like singular value decomposition, it's really quite beautiful what's possible. And in fact, it's hard to imagine a situation where you aren't going quite deeply into linear algebra very quickly. And so you see that's an example of a field that is accurately titled, but this field of artificial intelligence is guilty of being how can I say, quite bombastic, and people are very quickly jumping to claim things like they are getting close to general intelligence and so on, and I think we are not even near the fundamentals of that. Well, let me not go too broadly and actually commit the same problems that I'm talking about. Now, machine learning, of course, is extremely popular today, due in no small part, of course, to Python. But machine learning, it's something that's quite mature out there now, and it's one of the branches of artificial intelligence. And as you know, AI is composed of 6 main areas. And knowledge representation is one of the other areas. And my sense is that that's going to be the next important field in artificial intelligence, because what it allows you to do, what knowledge representation facilitates, is that you can make a problem machine readable. So we quite often rely on our understanding of things. So we might know a field well enough and we know about the relationships in that field. And we don't really encode those relationships. So knowledge representation can help you encode relationships and describe the entities at work in a process to the extent that it becomes possible to write generalized processing methods on that. So when you can convert a field into something that's so-called machine readable, you then bring all the power of computing into that. And with your creativity, you can unlock many interesting areas of analysis there. And then, of course, as I've mentioned, I will be outlining some of the bad experiences that I've had when there's inaccuracy in representing what is being done. And sometimes it's because the person doesn't really understand what problem they are working on. And in fact, I want to show a bit later that in this group, we are actually working on two main types of problem only, right? So we'll, by understanding that, we can look at classifying what we're doing, and that's a more rigorous way to collaborate among each other. And then we've talked about the machine readable part there. So that's the motivation for this topic. And here's the first experience. So singular value decomposition, of course, we know how important it is in terms of understanding what influences our the state of our system and so on. And I was really looking for a good resource on this topic to be able to teach it well. And I thought I had found a very good resource for this with a very nice example. So the authors of this blog, so it was a blog that I was reading this, which maybe should tell you something, but it was a blog where he was talking about the Netflix algorithm and about helping rank movies in terms of whether a person, well, you get the concept with the movies ranking, right? And in fact, that is a common example in understanding singular value decomposition. But even though the article was fairly well written, I just wasn't getting what he was what he was trying to present there. I couldn't understand the relationship between what he was saying and singular value decomposition, and yet it was written in such a convincing way. And he had written these claims about how his development actually promoted the whole field, and then after about 2 days of just reading and rereading and really struggling to understand what this person was saying, and obviously I blanked out his name here because I'm sort of criticizing him. After some time, I realized that what he was describing was simply interpolation. And I wrote to him and I said this, yeah, it seems to me this method doesn't really use SVD. So I said here, the most you can say is that this is SVD inspired in terms of the nature of the problem being solved. But yeah, and in fact, if you read this, I'm being much nicer to him than I probably was feeling after spending all that time. And then yeah, he latched on to the one good thing I said, which is yes, it's SVD inspired, and he says we do say that in part 4. Of course, part 4 is pages and pages into it, and when I looked at it, he didn't really say that. So, so this is an example where someone has misrepresented what he was doing in terms of the nature of the problem that he was solving. So, if you point out, if you are able to understand that the approach taken is interpolation, then we know how to do interpolation, right? We can easily bring in to bear all our interpolation methods and go ahead and solve the problem that's being outlined. But if we've misrepresented the nature of our approach, it's going to waste many people's time. It's going to cut you off from potential collaboration, and so that's one example where the approach was not properly represented. Then a second one is kind of very broad, right? When I started hearing all these terms, machine learning, then I thought, okay, now there's this whole other field that I have to learn. And from this background of chemical engineering and everything we've learned there, and it had started to grow on me that what we've learned in chemical engineering is actually quite deep and has applications in many, many areas, and that I could adapt most situations to our chemical engineering development, and I would be able to, by rigorously classifying things and adapting the theory, I could use that to solve many, many problems. And now suddenly there's this huge field, machine learning, and it looks quite glamorous, right? So this morning, I just typed machine learning into Google image search, and you can see all the pictures that come up here, right? So all these things that have to do with the brain and thought and human, development and all these, very promising things. So it looks like that. And also when you start reading into the field for the first time, you see tables with not just numbers, but tables with text and categories, and yet you have a model now that's working with that, and it looks magical. And you think, how did I miss this field? And what is machine learning, right? We are from this very stodgy world where y equals f of x and p. Now suddenly you have this. How did I miss this giant field? And in fact, when you read enough into it, you realize, well, machine learning is curve fitting, right? And if you do, if on Google image search again, if you type in curve fitting, this is what you get, right? You don't get nice pictures of the human brain and all that development. You get that it's just curves being put to points, and yet that is all machine learning is. So so we are going to look at, even though we are saying it in a kind of negative sense now, that and we are saying curve fitting means this, well, of course it's this means more than that. So we'll look at that. About half the group is actually working on problems of that style, but there are particular variants of that. But anyway, that was the second, I don't know whether to call it an experience, but that was a kind of general thing that happened over time. And in fact, even your neural networks, right? If you come back to this picture, right? All these claims about neural networks, and it is amazing what you can do with neural networks. But by the end of the day, the whole neural network is actually one equation, and we are just fitting the weights there. It is just about the same curve fitting that we are used to in chemical engineering. And then unfortunately, I didn't put in the bit about converting the categories or the text into numbers, but that can be done quite easily also. So if you have a list of categories, you just make new fields. So if you're in your column with categories, if you have maybe 3 categories, then you make 3 columns and you just say whether the object is 0 or 1 in terms of that category. So there's an easy way to incorporate categories as variables as well. So that's broadly on machine learning. Then in the third experience, this is now referring to the origins of the AutoScholar advisor system. So when I was a young staff member at UCT, we had all these processes that required a lot of manual work. And I wrote code just to automate my way out of having to do any real work, right? Due to a reluctance to do any work, I started writing the code. And then as I wrote that and people noticed how quickly certain things were being done, the interest grew in applying it in other places. So I had written the code to help me in chemical engineering. but then I got interest also at UCT from civil engineering and from other places, so they all wanted to use it. And then the problem was I had hard coded it for chemical engineering. So the question then was, how do I abstract that such that this method becomes generalized enough that you can use it in other places? And there was a way that we did that. And in fact, the person from civil engineering, who's now, I think he might be a vice chancellor somewhere, he sat over one weekend and he wrote the translation object that I specified to him. And on the Monday, it was working perfectly. So now that's okay inside one university. That's fine. But let's say now you've switched over from UCT and you joined UKZN. And so to use the same methods, I had to figure out a way to translate the methods into UKZN. And the way that I did that, given that the way UKZN stores its data is different to the way UCT stores its data. And by the way, we applied this at DUT as well. And they will have yet another way of naming their tables and structuring their database. So again, it was an approach of abstraction. And here, I also didn't want to do the work of writing this mapping. So I realized all I needed to do was to specify what inputs were going to be sent, what request was going to be sent for data, and in what form I expected the data to come into the AutoScholar. And so all I did was write an API spec, so an application programming interface. I wrote the specification for that. And here you can see it's telling you that when the AutoScholar asks for this particular data about the names of faculties, it will send a request called get college faculties ID. And it's going to send you a college code as well. And then you have to reply. So this is talking to the institution. You have to reply with an array of faculties with two attributes, a code and a label. And so if you just specify this, then, and I also gave sample code for how to do that. Then whatever name they have, however they've gone and structured their database, you don't have to bother with that. It's their business to go now and write this layer. So this layer, they write the code which will satisfy the specification. So this is another example of an abstraction where you can now suddenly gain access to all the methods available. So in the system, the AutoScholar, you have all these methods of analysis available. And all you need to do is declare how all those methods expect data to come in. And then you have access to all that functionality. So by analogy here, in our problems in machine learning and data science and otherwise, if we can abstract the problems to the point where we know what type of problem it is, suddenly you have access to all the methods available from those fields. And it's often the case that people working on a specific problem haven't even connected, haven't even made that basic connection. They are so wrapped up in the context of their problem that they don't realize that there are established ways of solving that problem, that there are many, many solutions to that problem. And in fact, that there are many pitfalls to that problem. And they can easily stray into one of those pitfalls and commit some of the errors that are rife in the field. So I'm hoping from these three outlines of experiences, you are starting to appreciate the importance of being able to place your work and classify it and formalize it. Okay. Now, here's further to that. We are talking here about fitting parameters. I put a latch on the door so he can't get in now. So here I'm talking about the simple case of fitting parameters to an equation. So let's think about this basic problem where we have Okay, sorry, 1 second. Okay, so so now let's say we are trying to fit the parameters. So we've got some data and we have some model output. So we've got some model which is telling us the model outputs. And so we want to choose the parameters P such that our model output is close to our experiment output. So that's a typical problem. And then if this equation is linear, right? If F happens to be linear, then that means we can write y equals all the inputs multiplied by the parameters. And then this has a nice solution. So if this is a matrix and that's a vector, then you have this solution. And that's a one-shot solution, as I say there, which means that you just calculate that once. And you see, x is fully defined. So this little bit of processing can always be done. So you just evaluate this and multiply this. So just by doing some simple multiplications, you have the solution. That's if the equation is linear. Now, if it's not linear, right, it's a much different situation. Then you need to make a guess for all your parameters. You have to search a space. It might be a high dimensional space. It's a terrible problem once you have to go and solve it in a nonlinear way. So we really love linear forms of our problems. We don't like nonlinear forms. So with that kind of introduction, I want you to look at these equations and tell me, are these linear or nonlinear equations, right? Maybe let's take them in turn. So maybe use the thumbs up. So get ready to use your thumbs up. So is this linear or nonlinear? So maybe use thumbs up if you think it's linear, and thumbs down if it's not linear, right? So clearly that's linear, right? So this one is easy. How about this one? We've got x cubed and x squared. Is this linear or non-linear? So everyone's shaking their heads, not even bothering with thumbs down. You're saying, no ways, that's not linear. Okay. How about this? So again, you've got x cubed, and here you've got the sine and x squared and everything. So linear or not linear? No, not linear, right? And then this one. Okay, so some are a little bit hesitating. You're thinking there's some trick to this, right? It looks like these three are clearly nonlinear. So all these are linear. These are all linear equations because you have to define the problem, right? Look at the problem we are solving. We are solving the fitting. We are trying to fit the parameters to this. And we said that we must be able to write our equation in this form: y equals x times p. Now you see, if you can recognize that these are all linear, then you have access to the solution, right? And so why do we say these are linear? Well, we said the first one was linear clearly. Now let's look at the second one. You've got x cubed, x squared, x, so this looks nonlinear. And yes, it's nonlinear in x. But x is not the focus here. What we are trying for is this thing, right? When we say linear, we have to be a bit more specific. It's linear with respect to p, right? So you see here, with respect to p, in this case, it's k1, k2, k3, k4. It's linear in these things. So we can easily imagine that we can rewrite this equation as x. Now we would have to modify x. We would create columns of x. We would create one column of x, which is x cubed. And you can imagine simply taking a set of x values and then just cubing it and then creating a column x cubed, make another column x squared, and then x, and then 1. And then, so then that's one matrix. So you have a matrix of all those columns, and then you create a vector of k's, and you basically have this form. And so you can easily solve for this. With one shot, you can fit this polynomial. So with respect to p, this is linear. Okay. Now, how about this one? Right? If you look at this equation, um, you guys should, when I drag this thing around, you should all be going, right, knocking about. Okay. So if you look at this now, it looks quite non-linear in the constant. Well, not these two, but you can see here it's sine of k2 exponential of k1. So that looks quite non-linear in k. However, we could create, we could just call it k1 dashed and say, let k1 dashed equals e to the k1. And let's let k2 dashed equal sine of k2. And then we create the columns x cubed, x squared, x, and 1. And then again, we have this nice form here, x times p. So you see this equation then, in terms of solving it, it's not going to be linear in p exactly, but we can find a transformation into a linear space. And then we can easily, once we've solved for those constants, k1 primed, k2 primed, we know how to get back to k1 and k2, right? We just invert it here. So that's a linear form. And then here, if yeah, you can process this equation fairly easily. This time you would have to involve y as well. But you see, you have values of y available to you. So if you now create for your x's, if your capital X is some combination of y and x, then those are new vectors. And then you can solve for these k's again. So that's another example of a situation where if you can accurately classify the problem, you then have access to a method which can solve that problem quite easily, right? In this case, it was very easy to solve the situation. Whereas if you looked at this equation as it was, your automatic reflex might be to go and use nonlinear solving, and then you are basically stuck in no man's land. It's still a terrible situation if you have to do nonlinear solving. Okay, so that was an example. And now let's do a review of our projects in the group, right? And as I claimed earlier, we have just two problems that we are working on in this group. So the first one, y equals f of x and p. And I guess you are each looking to see where you fall. Yeah, so I don't know whether to pause there and give you a chance to have a look at that. But yeah, so I would say there are 6 of us that are working on problems of this nature. And if let's talk about each project. So if we look at Samira, Christine, and Mopedi, so in each case, you are interested in the model itself. So consider Samira, she's trying to understand the nature of the mixing in that reactor. So she's trying to form a model that describes the conversion and the reaction rate and so on. Christine is trying to develop the kinetics. She's trying to create a description of the kinetic mechanism by which methane is oxidized. Mopedi also is looking at how do you hybridize, how do you combine the extreme, the inviscid flow and the opposite extremum, how do you combine them to get an accurate model? So those are all people trying to understand the physics of the problem. And then Pilani 2.0. So I've got Pilani 1.0 here and Pilani 2.0. So in his PhD study, Pilani is not so interested in the function itself, right? In contrast to these 3 people who are looking at the model, Pilani knows the model. It's a neural network. But in his case, he's trying to choose X. So Pilani wants to know, what's the best way that we can choose our X values such that we get very efficient training of the network? So in the fitting of the parameters, right? Training a neural network, it's just another name for fitting parameters of this type. So how do we choose these X's well? So we've got a massive bank of X values. We've got 20 years from a Sasol plant. So how do you choose X well enough out of the whole table of X's? How do you choose X so that you can fit P very easily? So that's what he's working on. And then Josh and Tobakile, you are working on, you've got scikit-learn, and you've got these models available like logistic regression, nearest neighbors, and so on. And you are interested in basically fitting your P. So you are looking for a set of parameters P, which then gives you a good match. So you are not looking at how do you efficiently choose X, but in your case, X has to be assembled from various sources. So so Josh, you've spent many months pulling together different data sources to assemble X, and Tobakila, you are in that same process now. And in fact, that's where I asked you to talk to each other as well, because you also use the same tools in GIS, right? So so your problem has quite a lot of work to do in terms of assembling X itself, and then your actual problem is in solving for P such that we have a good model, a predictive model, right? So that's the first class of problems. Then we have this other class of problems here, where there's some output variable that we are trying to extremalize. So I said min here, but it could just as well be max. So we are trying to extremalize some output subject to x's or p's. And in fact, most of you industrial symbiosis, in the industrial symbiosis, most of you are living in this space. So, well, let's talk about some examples here. So Sid and Pilani, for example, are looking at how can we find a path. So if you have two companies and you have a network of possible transfer routes, what's a good choice of route to connect those two companies? So maybe that's a bit more Sid. Pilani, of course, using Dijkstra and looking at navigating a state space. That's also about finding a path. So in this case, instead of parameters, these are points along a path, but you are basically fitting these parameters such that you maximize this y. So y might be a cost function in this case. So that's one. And then Delinsha, you are looking at minimizing how do I say, you are looking at minimizing the unmatched amounts, and you are creating binary sets. So in your stable marriage problem, you are trying to, you've got a group of entities, and you are trying to connect one entity in one group with one entity in the other group. So in your case, these sets are binary sets. They are going to be, you are going to allocate two things to each set. So that's in making a connection. And yeah, you are trying to minimize the unmatched amount. In Zamishka and Isaac, you have multiple entities. So you have all these documents, and you are creating clusters. So you have a cluster, and you can have any number of documents that belong to that cluster, right? So in contrast to Delinsha's case, where you have binary sets, yours are multi-entity sets, and then but it's in the same class of problems. And then Sudain, you are looking at, you have a process, and you can think of your process as a set. So in a way, well, we haven't defined the term entity yet, but you have a process, and that process can be thought of as a set of inputs and a set of outputs. So if your inputs and outputs are given by X, then you can say that X is directed. So some of those inputs are pointing into the process, into the set, and some are pointing out. So you are trying to derive the processes involved in a certain situation. And when you know, when you are able to do that, then you can figure out whether X is being consumed or it's being produced, right? So I'm not sure if you have some serious reservations about this, but this is my short sort of view of a simplified view of the problems that you are each working on. Now, of course, the actual solutions that you are applying may be quite different to this. You can't easily represent it just with two classes of things. But in terms of the problem, right, not yet looking at the solution, in terms of the problem you are solving, you can classify it in these two ways. And now each of you are deriving solutions to that class of problem. And it's important if you are able to classify your solution approach to that problem, then you see it exposes that solution method to other people who are working on that similar class of problems. Okay. Now, I actually think this is going to be a rolling series. I do have a fair bit more on how to represent the data itself, so the Y's and X's. There's a way to model that, and there's a way to represent it in a tabular sense. And in fact, you find there are some generalized things that you can represent, and there are ways to there are some serious problems that we've managed to solve along the way. But I think it's best we leave the data representation side of it to another session. I wasn't sure how fast I was going to finish the first part, so but I think it's a good place to stop. So generally to say, I hope this has explained better why I've been harping on about formalizing the problems and classifying what we're doing. And so, of course, we want to strip away the context and reveal the mathematical structure. We'll show later that the way the data can be represented also reveals features about the problem and the solution. And the overall goal is that we want to make our developments machine readable, right? Once they are machine readable, it becomes possible to automate the solution of problems. So we started out saying that our field is loaded with buzzwords and that many people are claiming moves towards general artificial intelligence and so on. So we are not claiming that we know we are going to do that, but this is a way to take steps in that direction. Start making problems machine readable, start making data machine readable, and then look at how we can automate and then we can start moving towards deeper analysis. Okay, so that's everything I wanted to cover there. Thank you for your attention.
Okay, thanks, Prof, for that. I think it was really informative. It also gave us a good indication on everyone and the projects that they are doing. And I think for us as a research unit, we understand better now the types of people that we can go to the people working on the similar problems to us. And I think it also helps us with clearly defining our problem and better understanding it from this perspective. It helps us when we research in concepts, when we trying to find better ideas and stuff. But I won't go too much into it. I'd like to firstly open the floor for questions based on the technical questions on the presentation or just any questions regarding what was presented today. Okay. I think I can't really see all of you guys' hands. Sorry about that. Just
Yeah.
Sedaine. Okay, I can see now. Sedaine.
Thanks, Josh, for that. Thanks, Prof, for the presentation as well. I think with you and I in our meetings when we speak about relational databases and setting up databases as well, and when you spoke about APIs, and we especially speak of when we as a group would set up an API for this operation, for when companies are actually getting involved and trying to communicate with each other. I noticed that it's kind of like when you specified that schematic of what you'd need for the API, it's you had like two very high level questions. They weren't so specific, but they were just very succinct, and it's exactly essentially what you needed. Yeah, just the action they get college faculty's ID and college code string. So even like in our case where we'd have to think of those kinds of questions which we'd have to formalize, since like we said, our problem in industrial symbiosis is the classification aspect of it and the text mining and so on, and then also the matching. So just to generate those kinds of questions for the broad scope of companies which may be in a cluster, I think would be challenging, especially since the project, the industrial symbiosis group, and the projects we're working on, it's, we're still kind of coming to terms with what our projects are and the extremities of it. So I think down the line, Prof, you're going to have to maybe guide us a bit more about setting up the API and those things.
So just to get into this a bit, this screen is not so much about the modeling process or about developing the problem. This is the step needed to access a method. So let's say you've created a method, like you've trained the model and you've put the model somewhere online. So you've set up a server, you are hosting that model on the server, and now you want to grant other people access to that model. And so the person, number one, needs to be told where to go to access that model in the form of a URL. So you give them HTTPS, whatever string it is. So that tells you, so you've got a URL. Then the next thing they need to know is, how do I query that URL? How do I instruct my system to go there and get college faculty ID? And in fact, I might, I'm not sure if I have opened here an example. I might have been working on an API somewhere. I think I'm still on share screen, right? So here's one example. So here is the URL. So in this call here, I'm just going to make this a bit bigger. Yeah, and by the way, I'll have to blur this out, but this is an address where my API is hosted. And here is an instruction, create entry. And I'm specifying it's a database operation. So it's not a call to a model or anything. It's just writing to a database. And then I specify some values. So this is clearly just a test thing. So I'm specifying some values to write to that database. So this is this has been written by a user on the client side. So someone on their device. When I say client side, that means on their device, on their computer sitting on their desk. They've written this, and that is going to go to this address. Now, when I say easy Ajax here, that's going to send that to that address. So it's going to translate that object into a string and send that string to that address. Then when it's received there, the point is that at that server, it will know what to do with this. So that server has been set up that it's looking for a part called action. And when it sees action equals create entry, then it knows what to do with that. So also F1, F2, it must know what to do with those things. So all I'm saying here is when you create your system expects data to come in a certain way to you. And once you've extracted the parameters from that call, then you take some action on that. So this is just a specification. It's just a declaration that my system expects you to ask me a question like this, and then I will respond in this way. I will send you an object back, which will have an attribute faculties, and in that it will have an array, and that array will be an array of objects with attributes, code, and label. So it just defines the structure of the data coming in and going out. And once you know this, then you can address queries to that API, and you will get responses that have been specified like that.
Okay, yeah, because the concern that I had, especially when when you spoke of a case where university databases, for example, they structure the databases and the data types may have been set up differently. In some cases, student numbers, for example, may be set up as serials, whereas other cases they may have been integers or whatever. So just a simple example, if you want to join or insert data into one table in your database from maybe another university's database, and the data within itself is structured differently, or is a different species of data, then it's a common SQL issue where you have that kind of correlation, or it doesn't really talk to each other well.
Yeah.
So I think with this, you can kind of fix that issue.
Yeah. So here we are saying, I don't care how you've called your faculties table. So at UKZN, you might call faculties schools instead, as we do, right? So we call them schools here. And the system is saying, whatever you call it, you know what I mean by faculties here. And there's other documentation, so it's clear that's what we mean by faculties. So at UKZN, they know, okay, I need to go to my schools table and I need to pull out the names there. And then I need to relabel that as faculties and then send that to the AutoScholar. So this just declares what it expects, and then it shifts the responsibility to the person who wants to use that system. So if you've created a model and you want someone else to use that model, then they've got their own way of doing things. And you're saying to them, well, I don't care. It doesn't matter to me. If you want to use my method, this is the program. So then they know how to extract their data. They know how to rename it such that they can use your method.
Okay, cool. Thanks, Prof. Understand now.
Maybe I can go next, Prof. Hi everybody. I've been watching all your seminars. I've watched yours today in Samishka, Delincia, the ones closest to mine. I also caught yours, Joash. I thought it was very good. I think I messaged you to say well done on that one. So Prof, and I think we've had like a couple of good meetings in this past few weeks. So what I've done now is I've tried to take a step back and do sort of what you're doing right now, where I'm trying to like take that step back and see, my project at a fundamental level, what questions I'm trying to answer, sort of agnostic of the methods, because as you say, I think I was starting to get stuck in my own problem and the own context itself. So I said, okay, I'm going to take a little step back. And that's also why I wanted to see, what everybody else is doing in the space and, get a bit of a bigger picture. So thanks for also, painting this bigger picture. I think it's very important because, we don't want to lead to sort of not necessarily duplication, but we're taking different approaches, but the question is sort of the same. And then maybe our methods sort of overlap in certain ways. And then it makes me wonder how, we're going to get to the end, or like, what's the best way to do this whole problem. So you come back, and I'm trying to look at that now. And I think as we're going forward, the data representation is also going to be very important. Like I saw towards the end, definitely, you said you want to take this to a different session. I think for myself, I've also been thinking about how to represent my data so that the methods become more easily, it jumps out of the representation. We're not trying to, look at such a granular level that we sort of miss the question itself and miss the data representation. So I think that's going to help us quite a bit. And I wanted to say thanks for that, more than a question, just a comment on that part. Yeah.
Great. Thanks for that, Isaac. With the data representation, in a way, it can be part of the modeling process, because quite often, as you're just browsing the data, you start to get more ideas about the modeling side. And what's interesting about it is that even though we think that there's any number of structures out there that any new context may have a totally different, how can I say, the data may be qualitatively different, fundamentally different, that we won't be able, that we have to apply our minds again to that data. It actually, when you start breaking that data down, there are in fact just about 4 main options that arise. And so there's a small and countable number of options that happen in the data. And once you know those options, it opens up the whole area of data exploration, because then you are not afraid of context anymore. Because currently it might be the case, maybe not so much in this group, but to someone thinking about data, And it can only be, I can't imagine someone not knowing this stuff, because how do you even imagine starting to model something when you don't know how to break down the data in a field? You see, there's a specific way to break down data into, and it's part of converting it to a machine readable format. And when you do that, you'll find that there are, you end up with relationships between data sets. And there are only 4 types of such relationship which exist. That means no matter how complex your structure gets, you are able to convert it into the small countable number of options which may occur. And so, yeah, that's kind of stealing our thunder a bit from the future ones. But yeah, once you know that, you have the sudden kind of euphoria that you develop this confidence that you can take any situation and you can classify it, and hence you can bring the full power of all the methods you have available to bear on virtually any problem.
Okay, I think are there any other questions directed towards Prof on the presentation? Okay, if not, we can also go to the second part of our presentation where we actually give feedback on the way that it was presented and the presentation itself. So are there any comments on that?
Yeah, again, similar to what I said to Delentia's presentation, Prof, these bigger concepts that are so much harder to understand, the fact that you broke them down, again, very simply for us to understand. But also something else, and also a comment about both the presentation and the general idea of what you were presenting. The fact that we are forced to think about sort of our global problems, to actually understand what it is we're trying to solve before just diving in and trying to code it and solve the problem. That's a huge thing for us. And this also, I know for me, it helped me understand where everything is coming from. And more than that, how all of our projects link together. So yeah, that was just a comment from me. That I found really helpful.
Thanks, thanks, Amishka. And I think we must have a rule here that, because I'm in the supervisor's role, we actually need a rule for this part that if you're going to say something positive, we need some criticism as well. So yeah. Do you have any points for improving on the presentation as well?
Maybe making this code block here bigger. I don't know, a bit more readable, maybe like a bigger size or something.
You've been very soft on me, Amishka. Okay.
Okay. Okay. Are there any other comments on the presentation? Okay, if not, I'd like to officially close this presentation. And Prof, thank you once again for presenting this topic to us and kind of broadening our understanding of the overall concepts and of what each person within this research unit is working on. Like I said before, it would significantly help us moving forward in our individual studies, especially with the discussions we can have amongst each other and just in the general research phases of our project. And we look forward to the upcoming sessions. Thank you.
Thanks so much. Thanks very much, everyone.
Thank you.
Thank you. Bye, guys.